The early days of grounding focused on static electricity and lightning protection. Utilities ground their systems to increase reliability and minimize voltage fluctuations. Utilities prefer multiple grounding points for redundancy and to reduce the likelihood of losing the return path. Utility grounding aims to protect personnel and the public from electrical hazards and ensure the proper operation of overcurrent protection devices. National Electrical Code, or NEC. Grounding also aims to prevent accidents and damage from lightning, transformer failures, and high-voltage-low voltage contact. A crossover with an ungrounded secondary system could lead to catastrophic consequences. Modern transformer design typically includes internal overvoltage protection to prevent this scenario. While grounding does not directly protect equipment from lightning transients, it provides a path for these transients to be safely dissipated. Bonding non-current carrying metal parts ensures a low impedance path back to the source to facilitate the operation of overcurrent protection devices. Electrical codes and industry practices outline the concept of grounding. While modern transformers have overvoltage protection, it is still common practice to ground the secondary system to provide an additional layer of protection, particularly in areas with high lightning activity. The choice and installation of grounding electrodes such as rods and plates are governed by local code and site conditions. Proper sizing and placement are crucial to ensure effective grounding. Grounding is an essential safety measure in electrical systems, serving multiple purposes. Firstly, grounding helps to stabilize voltage to earth during normal operation, preventing unwanted voltage fluctuations that can disrupt equipment and pose safety risks. Secondly, it provides a low impedance path for fault current to flow back to the source, enabling overcurrent protection devices like circuit breakers and fuses to quickly clear faults, minimizing damage and preventing electrical fires. Thirdly, grounding protects against electrical shock by ensuring that metallic enclosures and other non-current carrying parts of equipment are at or near ground potential. This prevents dangerous voltage differences that could cause shock hazards if someone touches a faulty piece of equipment. There are various types of grounding systems, each designed for specific applications and requirements. Equipment grounding connects non-current carrying metal parts of equipment to ground, providing a low impedance path for fault current. System grounding connects the neutral point of a power supply to ground, stabilizing voltage and providing a reference point for overcurrent protection. Electrode grounding involves using grounding electrodes, such as rods or plates, to establish a connection to the earth, dissipating fault current and providing a stable ground reference. Each type of grounding system has its own set of requirements and best practices. Equipment grounding requires the use of appropriately sized grounding conductors and proper bonding techniques to ensure a low impedance path. System grounding must comply with applicable codes and standards, including requirements for grounding electrode systems and grounding conductor sizing. Electrode grounding involves selecting and installing grounding electrodes in accordance with local codes and site conditions, ensuring that they are properly sized and placed for effective grounding. Proper grounding practices are essential for ensuring electrical safety and reliability. Regularly inspect grounding systems for damage or corrosion, and replace any components that are found to be defective. Test grounding systems periodically to verify their effectiveness and address any issues promptly. Ensure that all electrical work is performed by qualified personnel who are trained in proper grounding techniques and procedures. Grounding systems play a vital role in protecting people and equipment from electrical hazards. By understanding the principles of grounding and following best practices, it is possible to create safer and more reliable electrical systems. The effectiveness of a grounding system hinges on several critical factors. Firstly, the conductivity of the grounding path is paramount. A low impedance path allows fault currents to flow quickly back to the source, tripping over current protection devices promptly. Secondly, proper bonding ensures that all metallic parts of an electrical system are electrically connected, eliminating voltage differences that could pose a shock hazard. Thirdly, the grounding electrode system must be properly sized and installed to effectively dissipate fault currents into the earth. Furthermore, regular maintenance and testing are essential to ensure that the grounding system remains effective over time. Corrosion, loose connections, and other factors can degrade the performance of a grounding system, so periodic inspections and tests are necessary to identify and address any issues. In addition to the technical aspects of grounding, it is also important to consider the human element. Electrical workers must be properly trained in grounding techniques and safety procedures to minimize the risk of accidents and injuries. Education and awareness are key to promoting a culture of safety in the workplace. Grounding is not a one-size-fits-all solution. Different types of electrical systems require different grounding approaches. For example, a residential electrical system may have different grounding requirements than a commercial or industrial system. Similarly, a high-voltage system will require different grounding techniques than a low-voltage system. It is important to understand the specific grounding requirements for each type of electrical system and to design and install grounding systems accordingly. In addition to the NEC, there are other standards and guidelines that provide guidance on grounding practices. These include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the International Electrotechnical Commission, or IEC. These standards provide detailed information on grounding system design, installation, testing, and maintenance. Staying up to date on the latest standards and guidelines is essential for ensuring that grounding systems are safe, reliable, and effective. Grounding is a critical aspect of electrical safety, but it is often misunderstood. By understanding the principles of grounding and following best practices, it is possible to create safer and more reliable electrical systems. There are some common misconceptions about grounding that should be addressed. One common misconception is that grounding protects equipment from lightning strikes. While grounding can help to dissipate lightning energy, it does not provide complete protection. Lightning arresters and surge suppressors are needed to protect equipment from lightning damage. Another misconception is that grounding is only necessary for high-voltage systems. In reality, grounding is important for all electrical systems, regardless of voltage level. Even low-voltage systems can pose a shock hazard if they are not properly grounded. Grounding systems are subject to various codes and regulations that govern their design, installation, and maintenance. In the United States, the NEC provides comprehensive requirements for grounding electrical systems. The NEC is updated every 3 years, so it is important to stay up to date on the latest requirements. In addition to the NEC, local codes and regulations may also apply. It is important to check with local authorities to determine the specific grounding requirements in your area. There are several different methods for testing grounding systems to ensure that they are functioning properly. One common method is to use a ground resistance tester to measure the resistance of the grounding electrode system. A low resistance reading indicates that the grounding system is effective. Another method is to use a clump-on ground tester to measure the current flowing through the grounding conductor. A high current reading indicates that there may be a ground fault. Grounding is an essential aspect of electrical safety that should not be overlooked. By understanding the principles of grounding, following best practices, and complying with applicable codes and regulations, it is possible to create safer and more reliable electrical systems. The NEC specifies requirements for grounding and bonding to ensure electrical safety. Article 250 covers grounding and bonding requirements for electrical systems. It outlines the types of grounding systems permitted, grounding electrode requirements, and bonding methods. Section 250.4 specifies the general requirements for grounding electrical systems. It emphasizes the need for a low-impedance ground path to facilitate the operation of overcurrent protective devices. Section 250.24 covers grounding of service entrance equipment. It requires that the service neutral be grounded and bonded to the equipment grounding conductor. Section 250.50 specifies the requirements for grounding electrodes. It outlines the types of electrodes permitted, such as ground rods, metal water pipes, and concrete encased electrodes. Section 250.104 covers bonding of metal water piping systems. It requires that metal water pipes be bonded to the service grounding electrode to ensure electrical continuity. Section 250.118 specifies the types of equipment grounding conductors permitted. It includes conductors such as wire, cable, and metal raceways. Section 250.122 covers sizing of equipment grounding conductors. It provides tables for determining the appropriate size of grounding conductors based on the rating of the overcurrent protective device. Section 250.166 specifies the requirements for grounding separately derived systems. It outlines the methods for grounding systems such as generators and transformers. Understanding and adhering to the NEC requirements for grounding and bonding is essential for ensuring electrical safety and preventing electrical hazards. Effective grounding systems rely on multiple components working in harmony to provide a safe and reliable electrical path. Firstly, grounding electrodes, such as ground rods or plates, establish a direct connection to the earth, providing a low resistance path for fault currents. Secondly, grounding conductors, typically made of copper or aluminum, connect the grounding electrodes to the electrical system, ensuring a continuous path for fault currents to flow. Thirdly, bonding jumpers, which are short lengths of conductor, connect metal enclosures, raceways, and other non-current carrying metal parts, creating a common ground potential and preventing voltage differences that could pose a shock hazard. Furthermore, overcurrent protection devices such as circuit breakers and fuses are essential for quickly interrupting fault currents, minimizing damage and preventing electrical fires. The proper selection, installation, and maintenance of these components are crucial for ensuring the effectiveness of a grounding system. Grounding is not merely a theoretical concept, but a practical necessity in real-world electrical systems. In residential buildings, grounding protects occupants from electric shock by ensuring that metal appliances, electrical boxes, and other conductive surfaces are at or near ground potential. In commercial buildings, grounding safeguards equipment and personnel from electrical hazards, preventing damage to sensitive electronic devices and minimizing the risk of electrical fires. In industrial facilities, grounding is critical for protecting workers from electrocution and preventing equipment failures that could disrupt production. Grounding also plays a vital role in protecting against lightning strikes by providing a path for lightning energy to safely dissipate into the earth. In all of these scenarios, proper grounding practices are essential for ensuring electrical safety and reliability. To maintain an effective grounding system, regular inspections and testing are essential. Firstly, visually inspect grounding conductors, connections, and electrodes for signs of corrosion, damage, or looseness. Secondly, use a ground resistance tester to measure the resistance of the grounding electrode system, ensuring that it meets the required standards. Thirdly, perform continuity tests to verify that all metal enclosures, raceways, and other non-current carrying metal parts are properly bonded together. Furthermore, regularly inspect and test overcurrent protection devices to ensure that they are functioning correctly. Address any issues promptly to prevent the grounding system from being compromised. Regular maintenance and testing are essential for ensuring that grounding systems remain effective over time. In addition to the NEC, various industry standards and best practices provide guidance on grounding electrical systems. The IEE provides standards for grounding electrical systems, including recommendations for grounding electrode systems, grounding conductor sizing, and bonding methods. The National Fire Protection Association, or NFPA, publishes codes and standards related to electrical safety, including guidance on grounding and bonding. The International Association of Electrical Inspectors, or IE, provides resources and training for electrical inspectors, helping them to enforce grounding and bonding requirements. Adhering to these industry standards and best practices can help to ensure that grounding systems are safe, reliable, and effective. Proper grounding is a cornerstone of electrical safety. It's a multifaceted system integrating elements like grounding electrodes, conductors, and bonding jumpers. These elements, working in tandem, establish a safe path for electrical faults, safeguarding against shocks, fires, and equipment damage. Adhering to the NEC guidelines, coupled with regular inspections and maintenance, ensures the long-term effectiveness of grounding systems. By promoting a comprehensive understanding of grounding, we cultivate a culture of safety, minimizing risks and fostering secure electrical environment. Grounding is also critical for sensitive electronic equipment, preventing data loss, malfunctions, and other problems caused by voltage fluctuations and electrical noise. In healthcare facilities, grounding is essential for protecting patients and medical staff from electrical hazards, ensuring the safe operation of medical equipment and preventing interference with sensitive monitoring devices. In telecommunications facilities, grounding safeguards critical communication systems, preventing service disruptions and ensuring reliable communication networks. Grounding also plays a vital role in renewable energy systems, protecting solar panels, wind turbines, and other equipment from damage caused by lightning strikes and voltage surges. In all of these specialized applications, proper grounding practices are essential for ensuring the safe and reliable operation of electrical systems. There are several common grounding mistakes to avoid. Firstly, neglecting to properly size grounding conductors can compromise the effectiveness of the grounding system, preventing it from safely carrying fault currents. Secondly, failing to adequately bond metal enclosures, raceways, and other non-current carrying metal parts can create voltage differences that pose a shock hazard. Thirdly, using improper grounding electrodes or failing to install them correctly can limit the grounding system's ability to dissipate fault currents into the earth. Furthermore, neglecting to maintain grounding systems can lead to corrosion, loose connections, and other issues that degrade their performance. Avoiding these common grounding mistakes is essential for ensuring electrical safety and reliability.